Okay, today in section 2, we want to be able to classify an exponential function as representing growth or decay based on our equations we were dealing with, and then calculate the growth of the investments under various conditions. So with that, we had our growth and decay formulas, and we're going to even break that down into talking about exponential functions now. If you remember from yesterday, let's just put them up here. We had n equals c times 1 plus or minus, depending on if it's growth or decay, r to the power of t. Now if you look at that equation, it sort of mirrors what we have right here. I'm just going to write it in its form. We're going to tell you that all exponential functions will be in the form y equals. So we're going to start with our answer equals some value a times a b value to some exponent. And so the equation we were using yesterday looks a lot like it. It was just using different variables. So if we know that we have a growth situation and we know what that growth is, then we were expecting now, today, our b value to be that number that's bigger than 1. If we know it's absolutely a decay situation, then we will be expecting the b value to be less than 1. We have up here also that a cannot be 0, because if a was 0, think about it, it would wipe out that whole equation. 0 times anything, gone. B is greater than 0. We said it has to be some exponent, and we're mostly going to be dealing with positive exponents, positive whole numbers actually. And we're also telling you B is not going to equal 1. So there will be some kind of change taking place, either growth or decay. As before, x is still the independent variable, so y is the dependent variable. B will be that growth factor. And remember, growth factor is sort of misleading for its name because that can be either plus or minus, like we were talking about up here. Not the value b, but the value that would go in there would dictate that our growth is bigger than 1 or less than 1. Therefore, it's a growth situation or a decay situation. Then a, we're going to call our y-intercept. We might even call it our original value when we talk about the equation here in a minute. So we didn't do anything with graphs the other day, so we are going to graph these. And what's going to happen here momentarily on our next slide, you will see that these graph into a curve quite a bit different than those parabolas we were seeing last chapter. So let's move on and let's try that. Oh yes, exponential growth and decay. So if you can talk about what you know about it growing and decaying, let's come back to that after we do a little graph. And I know I have a graph. Oh gosh, I know I have a graph here somewhere. Okay, so if I'm not finding it, let's go back and let's go to that slide we had it on, and let's do a quick clean me off and do a graph just so we can see. Okay, so if we have an equation y equals ab to the x, let's make it as easy as possible here. Let's say y equals 2 to the x power. If y equals 2 to the x, then normal graphing, we got our xy table, and we want to get a few points that are in there. No big deal. Positive, negatives, and 0 maybe for our exponent, but I think we said our exponents have to be positive. So let's just go 0, 1, 2, 3, because that's our x value. So let's go. When 2 goes to the 0 power, it's a 1. When 2 is to the first power, we get a 2. 2 is to the second, we get 4. 2 is to the third, we've got an 8. Now a quick graph, since those are all positive, we're going to start here. See what this thing looks like. Now I did not put any fractional values in, but we could do that. We also, I thought, said our x values were going to be positive, so that's why I didn't put any negatives or fractions. But if we have 0, 1, if I have 1 and then 2, and then I have 2 and then 4, and 3 and 8, it's not even going to fit on my little graph. If you would graph the situation in its entirety, and let's just put a couple in because we know how to do this, we've done negative exponents. If I would put 2 to the negative first power, you're not thinking negative numbers, you're thinking reciprocal. Flip me. So 2 to the negative first would have given me the number 1/2. So let's just graph that just to get a full picture of what's happening here. If I go -1 and I go up 1/2, okay, it didn't seem to grow as much as it did out there. If I put a -2 in, -2, remember the flip me reciprocal rule, so 2 to the negative second is really 1 over that, so 1 over 2 to the second, 1/4. And so we're coming over here and we're saying 2, and that's 1/4, it's half of that. So we're starting to see that we're going to get, let's make it a little thinner here, come and sit right in here. We are going to get a curve that keeps getting closer and closer and closer to that y or x-axis, and then our curve comes up and it's going to be shooting up like that. So our exponential curve, when it was growing, because that's what we're doing here because of the b value, goes up. We have the exact same combination, and let's just do it in blue, if we would have been doing a decay, and it would come down that same sort of way. So a growth and decay, very similar equations, very similar looks, but one goes up, one goes down. So when we say, oh, let's now write some characteristics, because you experimented with the graphing in section 6.1, then we should be able to talk about those exponential curves. So on a short list, we know that if it's a growth situation, so G for growth, D for decay, and both of our equations have that general pattern, what could you say? Well, you can see I did the generic stuff. A can't be 0, that's by definition. B can't be 1, and B is not 0 as well. So what else did we say? And now one thing, most of you would say, well, we know if it's a growth situation, B has to be greater than 1. If it's a decay situation, that same B value has to be less than 1. But bigger than 0 is what our number has been so far, so let's do that. So B is less than 1, but greater than 0. Keep adding to that list. That's what we're talking about. What else is there? You could say it graphs into an exponential curve. We just stated that on the other. Does an exponential curve have slope? No, neither did a parabola. But if you say it graphs into an exponential curve, you want to probably be able to say as a growth, it starts low and goes high. As a decay, it starts high and goes low. So have some characteristics. Now, add to each of these. What else would you add? Because as soon as you put a graph into play, we can start talking about lots of things, like what is, the x-intercepts, the y-intercepts, the domain, range, things like that. And I believe that's what this next slide was about. So if you sit there and list them all, double check. The domain on all of those would have been all real numbers, looking left and right. So when you look at your growth situation and you look at your decay situation, we would have had all real numbers. The range, positive reals, because remember, if I put a axes in there and we have a growth situation, it's crossing the y-axis, but it never crossed the x-axis. It got very, very close and never touched it. The y-intercept of each was that a value. So that's why we called it that original starting point. What is the value of your situation at 0? That's what we're talking about. The graph never crosses the x-axis. We said that. Exponential curves have no x-intercepts. They have a y-intercept, though. In one of the two quadrants, the graph gets closer to the x-axis. The x-axis is then the asymptote of the graph. Remember, we had that earlier when we were talking about hyperbolas. So right now, this x-axis would be the asymptote, where the graph seems to approach but never crosses, never touches. Constant growth, it's greater than 1, so x increases, the value of the function decreases. So we're talking right now, as x increases, the y value is decreasing. And you could do the same thing if it was a decay situation. So we have really talked about all of these, but they are key pieces to your graphs. Next, compound interest formula. If you look at it carefully, you've seen it before, probably used it in Algebra 1, maybe even geometry a little. But if we look at this, and I'll just, let's go with the actual values. So up here, y equals, the p is like our a value in exponentiation. That whole parenthesis again would be like your b value, and that nt power is like our x. So we have that compound interest formula really mirrors an exponential situation. Remember, compound interest formula, a is the total amount of money after the compoundings, p is the principal or the amount invested, r is the annual interest rate written as a decimal, n is the number of compoundings in a year, and t is time in years. So with that formula, you should be able to do several different situations. So let's just review quickly. Quarterly. If I said your bank was going to compound your account quarterly, what is that in terms of number of times in a year? You better be thinking 4. Monthly, 12. Weekly, 52. Daily, 365. And you can go and figure your hourly and by the second. And of course, I sort of skipped here. We would have even had them by the minute if you wanted to. Now, most banks are only going to do compoundings when? Think about that. Based on you have an account, you have a savings account, a checking account, something like that. When does your bank give you credit if you are earning interest on your account? And most of you would say they will do it monthly. So there's not too many situations that's going to give you in a bank, checking, savings account situation more than monthly interest. These other ones you could get in day trading, other types of trading, other investments. You could get some of those. Now, quick equation. Let's just say if we were doing quarterly, then we'd have our p-value. We have 1 plus, let's just say our percent is 5% right now. So we'd put that percent in as a decimal, 0.05. N, we're on the quarterly one, so that's 4 to the power of 4 times whatever t is, however many years we're going to let it invest. And let's say again that was 5 years. So if we have 5% interest, 5 years, we're looking at an equation that sets up like that. Hopefully they'll tell us how much principal. You should be able to use your calculator and handle that. You should not have to calculate that by hand. So lots of different choices there. Now, there is something called an effective yield. How much is your bank account really effectively earning? This used to be something that they had to post, but it is the annual compounded interest rate that yields the final amount of your investment. If you quickly did $1, 12 compoundings for 1 year, annual interest rate, you would find out about how much your account is really earning. And we'll probably do that one together in class. The book uses this example as use some trial and error or exponential regression equations to figure out R if it's not given. So if I gave you your invested amount, what it turned into, what you invested originally, the number of compoundings and the time, so I gave you everything but R, you'd have to undo that equation. It gets a little complicated, but you could undo that. Or you could use exponential regression. And we've done quadratic regression and linear regression, so you know where to find that. Again, there's an example in our textbook like that. Last thing we want to mention is transformations. We've seen before, and I put the page number up here again so you're focusing on it. When we move or transform any of our shapes, so now we have this exponential curve that we could slide, we could expand, we could compress it, we could stretch it. There's a bunch, way more than just the two that I've put here as a reminder, on page 138 in a chart. And again, hopefully we have them memorized, but we haven't used them in a while, so revisit them. So it was all about our function notation. So on this one, I'm looking for what's my parent function, and then if there is some multiplier out front, and that a value out front that's being multiplied is bigger than 1, then I know my final result will be a vertical stretch by a factor of that a value. Another example would be the same thing, but what if that a value is not greater than 1? What if it's between 0 and 1? Then we're getting a compressed view of our original graph by that same factor of a. So these are just two of them. They are two of them that they're going to use. They'll ask a few others. So if you need page 138, don't be afraid to go back there and look up your choices. Now, below the dotted line is something totally different. It looks like it's related to it, but they just say tell whether it represents a growth or decay situation, then give the y-intercept. Now, if you knew that f of x, the function, was equal to 2 to the power of x, you should be able to tell me right now that that's a definite growth situation. But now they're saying take that parent function and compare to what you see here. So they want to say, okay, we're taking f of negative x of that same situation, and you're multiplying it by 1/2. So if you want to put that equation into your calculator or to graph it, that'd be one way to do these. Some of you know what your y-intercept is here. So if we're doing this transformation, does it really move off of that, or does it affect it similar to maybe one of these? Because we're looking up here and saying, oh, that probably matches that situation right there. It's a multiplier out front of the original, but we do have that negative on the x, so what's that going to do? So just to give you an idea, you're playing around with your calculator, and we'll talk a little more about this in class. This first one, it should have been a decay once you did that 1/2 combination, and it should now go through 0, 1/2. Remember, this would have been a value of, put a 0 in, you get a 1. So your original value was 0, 1, and if it says we compress it by a factor of 1/2, if my y-intercept used to be at 1, my new y-intercept is now at 1/2. So a little more looking at things. There's a lot of choices here in this section, a variety of different styles, money, investment problems, graphs. So they threw quite a few different things in. We are going to only spend, I believe it's 1 day on this. So pick up what you can. Some of it will be carried over from, like, for example, page 138. But I think you'll be able to do most of the problems. But bring any questions you have, maybe about the calculator and the regression, things like that, to class with you, and we'll discuss it.